Imagine one person coughing in a crowded room. Within weeks, that single cough could reach millions. Viruses don't need passports, money, or technology. They only need us. How does something invisible spread so fast? The answer lies in simple mathematics, combined with human behavior. This is the story of how a virus conquers the world. Every epidemic starts the same way, with one person. Patient 0, the first known case. They might not even know they're infected. An invisible passenger, a silent hitchhiker. Each time they breathe, talk, or touch a surface, tiny viral particles enter the environment. One person infects 2, 2 infect 4, 4 infect 8. The chain has begun. But how fast does this chain grow? Scientists use a number called R0. R0 tells us how many people one infected person spreads to. If R0 is 2, each person infects 2 others. If R0 is 3, each person infects 3. Measles has an R0 of 12 to 18. COVID-19 started with an R0 of about 2 to 3. Seasonal flu sits around 1.3. When R0 is above 1, the virus spreads. When it drops below 1, the outbreak fades.
Here's where it gets terrifying. With an R0 of just 2, after 10 rounds, one person becomes over 1,000. After 20 rounds, it's over 1 million. After 30, 1 billion. This is exponential growth. It starts slow, almost invisible. Then suddenly it explodes. The classic hockey stick curve.
Epidemiologists model outbreaks with 3 groups. S, susceptible, people who can catch the virus. I, infected, people who currently have it. R, recovered, people who've beaten it. Everyone starts as susceptible. As the virus spreads, people move from S to I, then from I to R as they recover. The curve rises, peaks, then falls. This is the classic epidemic curve. Understanding this curve saves lives. Viruses have many ways to travel. Respiratory droplets from coughs and sneezes. Aerosols, tiny particles floating in the air. Direct contact, handshakes, hugs, kisses. Contaminated surfaces, doorknobs, phones, railings. Some viruses spread through water or food. Others through blood or bodily fluids. The route determines how fast it spreads. Airborne viruses are the fastest travelers. Not everyone spreads equally. Most infected people pass it to 0 or 1 other. But a few spread it to dozens. These are superspreaders. One choir practice infected 52 of 61 members. One wedding became a cluster of over 100 cases. The 80-20 rule often applies. 20% of people cause 80% of spread. Finding superspreaders is key to stopping outbreaks.
How do we slow the spread? Social distancing keeps people apart. Masks block respiratory droplets. Hand washing removes surface contamination. Quarantine isolates the infected. Contact tracing finds who's been exposed. Travel restrictions limit geographic spread. Each measure reduces R0. Combine them, and R0 drops below 1.
Vaccines are the ultimate weapon. They train your immune system to recognize the virus. When enough people are vaccinated, the virus can't find new hosts. This is herd immunity. For measles, about 95% need immunity. For COVID-19, estimates ranged from 70 to 90%. When herd immunity is reached, even unvaccinated people are protected. The chain of transmission breaks. Let's look at real numbers. The 1918 flu infected 1/3 of the world. HIV has infected over 80 million people since 1981. COVID-19 infected hundreds of millions in just 2 years. Measles, before vaccines, killed millions yearly. Smallpox killed 300 million in the 20th century. But we eradicated smallpox with vaccines. Polio is nearly gone too. Science gives us the tools to fight back. So how fast does a virus spread? One person to millions in weeks. Exponential growth driven by R0. Containment measures slow the spread. Vaccines create herd immunity. Understanding the math helps us prepare. Knowledge is our first line of defense.